Good morning. I'm going to go over this proof first, which should give you some insight into problem number 2 on the homework that's due 9/14. So let's look at one of my favorite proofs. You know you're a nerd when you have a favorite proof. That the square root of 2 is irrational. First step in proof writing is to write that as an if-then statement, a conditional statement. So if n is equal to square root of 2, then n is irrational. Write down the no, n is equal to square root of 2. Write down the show, n is irrational. Unfortunately, if you look up irrational in the index, and the definitions on page 16, it just says it's a number that's not rational. Well, that's pretty annoying. That doesn't really give me anything to work with. If they had told me rational, the definition for rational is much easier to work with. So that leads me to believe that this should be a proof by contradiction, because I just wished they hadn't asked me this thing right here. I had wished they had asked me then n is rational, because that definition is easier to work with. So this is not a contrapositive but a contradiction, because I just wish that this part here, the conclusion, was different. And the definition of rational means that I can express n as p over q, where p and q are both integers. So that definition is something I can work with, I can get my hands onto. So that's the trigger, that I wish that the conclusion was different, that it was the opposite. It's a black and white, it either is irrational or not. So that's a trigger word, that it's a proof by contradiction. It's not a trigger word that you should walk out of the room because you're upset. Assume on the contrary. So here's our proof by contradiction. I went over a proof by contradiction as our first proof in the term. I'm going to assume on the contrary that square root of 2 is rational, so it can be expressed as p over q, where p and q are integers. And I'm also going to make a further assumption that it's in its lowest reduced form. I can make that assumption that if it's not in its reduced form, I'm going to reduce it. So that means that p and q have no common factors, because if they did, I could reduce it further, right? So this is square root of 2 expressed as a fraction in its most reduced state. Well, I can do some playing around here. Then I can cross multiply that expression and square both sides. Well, that means 2 divides p squared by definition of divides. I dug in the book. I did the Jake Perry method, and I looked in the book and I found a theorem, and it's actually a famous theorem, that says if I have a prime number, which 2 is a prime number, and it divides a product of two things, in this case it's the product of p and p, then 2 must divide p, or 2 must divide p. I just copied and pasted corollary 11.4 with the letters they have in the book with my letters, which were the A was P, the B was Q, and the prime number was 2. So that means 2 divides P. Well, that means I can express P as 2 times R for some R in the integers. Now, I'd like to back up a moment here. So I look at this as a goal. I'm trying to write a proof. Everything in the book, as long as it's not circular, I'm allowed to use. It's a fact I'm allowed to use. Maybe I didn't prove it, but someone else proved it and left it there sitting for me. Dr. Williams thinks it's important for you to prove every detail. It's really, really important to do so, and my way is not the best way. So what Dr. Williams would like you to do is to actually, if you're going to use this theorem or this corollary, she would like you to supply that proof to her in the in your work. So that's not hard. It means that you actually go to the proof of the corollary and just pretty much copy paste, but put in any gaps that might be in the book, and make sure you have that. Emily Curry and I have been proponents of the lemma, so we put the proof of this corollary somewhere else in appendix and say, hey, I proved it, it's in the appendix, and I'm going to use it. However approach you want. If you're in my section, I don't need you to prove it. Doesn't mean I'm right. I have a sinking feeling I'm not right. If you're in Dr. Williams' section, you will have to prove this. In my section, we're not. We're going to pull it. I think I'm the lazier of us. So here we have, now I'm going to take this P equals 2R and go back up to this formula right here, Q times square root of 2 is equal to P, and I'm going to replace the P with 2R right here. And I'm going to do the squaring both sides again. If I square both sides again, I get 2 times Q is equal to 4 times R squared by squaring both sides. Well, if I divide the 2 out of both sides, that means Q is equal to 2 times R squared, so 2 divides Q as well. Well, now I got a problem. We just showed 2 divides P, and 2 divides Q. So that means 2 is a common factor of P and Q, but P and Q weren't supposed to have. I'm just copy and paste. I copied and pasted from the beginning. P and Q is in its lowest form, and they'd have no common factors. So now I've just arrived at a contradiction, a flaw in my logic, and my original assumption that I started out with, where n was rational, is false, and the opposite must be true, so n must be irrational. So it's like it seems like some sneaky way to come through the back door and prove this. I still got in the house, didn't I? So that's the proof of square root of 2 is irrational. Now, let's look at your homework. There's homework 3. Let's pull it. Taking a sweet old time, let's go over to this problem here. Prove that the product of an irrational number and non-zero rational number is irrational. I'm asking you to go to page 16. I think I already have it in my video here. Go there and look at that definition. Write it down in your notebook. Even though I've just showed it to you, doing it yourself is important, because what you're going to see when you physically write down the definition of rational number, you'll see that that's something you can manipulate and work with, while irrational numbers kind of just not being rational, which is not helpful. Cite that page number in your notebook, even though I've showed it to you already, because doing so is going to solidify that in your mind. I already talked about which definition is easier to work with. Rational is easier to work with than irrational. And now you're supposed to prove that the product of an irrational number and non-zero rational number is irrational. Write that as an if-then statement. That's step 1. You're going to look at that conclusion, and very similar to my conclusion, your conclusion is going to be vague, so you're going to apply a proof by fill in the blank. So that should get you started. Go as far as you can with that proof guide. We had a cadet who just had to go on trip section, and he was able to do it. So he's just like everybody else. He's not like he doesn't have like a nuclear thing on his head where he's superior to everybody else. Just like myself, we're just regular people doing heroic things like proving stuff about irrational numbers. Okay, so if you are either section, you can text me if you need help, 973-224-2562. And if you want to contact us by email, either one of us, that's fine. And we're here, I'm here all day till about 1600 today when I go to the rugby practice. So I'll be at rugby practice at 1600. All right, signing off.